Assalamualaikum and good day everyone. Now we have reached our week 4. Okay, we shall touch about what should be covered in our week 4 is the potential difference, and energy density. Okay, I will covering, okay, or summarize, okay, what is will be covered in the Tzadiku book from page 144. Okay, I highly recommend you to read the Tzadiku book because they have much detail, and I will do a summarization of what that should be learned by you guys. Okay, okay, now in a system, okay, in a system we have, in a system, let's say we have an energy exchange. Involving a charge, okay, involving charges. So naturally, you know that in a system we can have either one of the two conditions, okay, where we can have the energy exchange done by the system, and the next one is the energy exchange done to the system. So here the energy exchange happens, okay, by itself. We just observe, okay, we didn't do any things to that system, okay. However, in here to the system we actually introduce some external factor to the system. So here we will apply it, okay, we will apply some external factor. Okay, here first we divide this into two different distinguished different systems, which is done by the system, second is done to the system. Okay, imagine that you have a path from point A to point B, okay. This path have an passing through of electric field of vector E. Again, what is vector? Vector is a quantity having magnitude and direction. So you can see the E field is from A to point B, and let's say we have another of it and we have another of it. Imagine that you have a point charge here, when the point charge here a point charge is located in this sampling distance inside an electric field, it will experience a movement. Okay, movement, and force is created. Okay, so you see your E is here, this is your point charge. Let's say we can put Q, then you have the force in the same direction. Okay, you may have learned from your secondary school or in your foundations that when you have F and you have a distance, it will result in an energy. Okay, so here when it moving from here to here, it will have a small distance of dl. So the work done, the small work done by the system experienced by the Q, okay, you have your work done, small work done equals to F dot dl. Okay, F is your force and dl is your differential displacement. Okay, the movement from here to here. So judging by this, you should know that this is a vector, dot with a vector, then you result in a scalar energy. Okay, in your previous lecture, you know that actually E is equals to F over Q. Am I right? Rearranging this, you will have F equals to QE. Then substitute inside here. You have dW equals to QE dot dl. Remember, this is just a small energy. Okay, what if you want to have the total work done? So we have to have an integration. Okay, so we have to integrate dw, we will get w, then integration of QE dot dl. They say this is your equation 1, and you see the work done here is the total from getting the point charge from point A to point B. So you have to know your limit. Okay, the low limit and the upper limit. now we move to the similar case, but in this situation we apply, okay, we apply the external factor. So similarly, for example, imagine you have point A and point B. The same electric field flowing to this direction. However, now in contrast with this case, we apply the force we applied to the system, so that the point charge is now moving exactly totally opposite direction. This is your Q, so totally opposite, okay, because this is external factor. In contrast with this is the force by the system. Now here, because we apply external factor, so our force here will be external, okay. Here you can use external, or you can also use F applied, mean applied force, okay. So I choose this one. And then imagine when it starts moving, it will also have its own differential displacement, okay. Similarly, here we want to obtain the work done, but in contrast, now this, instead of work done by the system, this is work done to the system. Okay. So here is external, dW external. So we have F applied dot dl, okay, vector. So now we try to obtain our F, okay. We try to replace this F with our E related equation, okay, electric field intensity equation, just like this one, okay. So if you notice, for your E, it is moving in the opposite direction, right? So you have F applied over Q, okay. So rearranging this, you will have F applied equals to negative EQ, okay. Why is it? Because it's moving totally in the opposite direction, okay. Similarly, to get a total work done, you have to integrate this, okay. Before that, substitute first. So the total work done to the system, okay, is W integration of negative QE dot DL. In this case, the charge is moving from point B to point A. Okay, if you notice, based from equation 1 and 2, they are exactly the same. Only the direction is different. Okay, here you have negative here, and here you have a positive. Next, we will go to the potential difference. So before we go to the potential difference situations, okay, we need to know what is the definition of potential difference. Okay, potential difference is the work done or potential energy required per unit charge by an external agent in moving charge Q from point A to point B through an electric field. Okay, so it is actually the work done. Okay, the key point required by external factor in bringing a point charge from point A to point B, okay, through an electric field. So this is the key point. You may read inside Sadiku, okay, for the complete definition. Similarly, as I was mentioned, it is on the page 144 of Sadiku with the section of electric potential. Okay, without further ado, okay, by the definition just now, it is actually work done to carry a point charge from location A to location B through an electric field. So here, actually, so taking that potential difference is V from point A to point B, okay, in bringing a point charge. Okay, work done in bringing a point charge, so W, work done in bringing a point charge, Q. So because a point charge, okay, so this will be 1 afterward, because based on the definition is a point charge. So what we have learned from the previous lecture just now. Okay, what is your work done? Your work done is actually the integration of A to B E dot dl. So because it's unit charge 1, so you have there's a negative here, so you have E dot dl. Okay, you can see here. From point A, from point B, okay? So you must be asking that why we have E here, why we have negative here? Because we exert or we introduce external factor, okay? I mean, this is not happen naturally. We are trying to move the point charge, okay? A point charge from a particular position to a particular position. It does not happen naturally. We introduce the external factor. So that's why we have the E. Just like in the case that I covered in the previous lecture. So now you have this equation of potential difference A, B, negative E dot dl, okay? So when you see this, you know that this is your beginning point. You begin here, then you will stop here, okay? Means this is your final location. When you solve this equation, you will have in two values, okay? If you have the negative potential difference, means there is a loss of energy, loss of potential energy, when you are trying to bringing the charge from point A to point B. This means that the work done by the system. In contrast, if you have the answer in positive value, means instead of losing, you will have a gain of potential energy. So this means that the external factor do the work, okay? Means it's not by the system, but it's to the system. Okay, so what have you learned in your previous lecture about E? E can be described as Q over 4 pi epsilon naught r square in r direction. Okay. So let's say you want to introduce this to further expand this condition. Okay. Imagine that in this case, let's say you are using spherical coordinate. Okay. Imagine that you have a spherical system, spherical coordinate. And there is a charge here. Just for simplicity, you put at the origin. Let's say the question is asking, what is the potential difference between point A? For example, let's say you have your point A somewhere here, and you have your point B somewhere here. Okay. Imagine if there is question asking, determine the potential difference between point A and point B in a region in free space. Where an electric field E exists to a point charge. Okay, here our point charge at the origin. Okay. So what is the potential difference? Before that, we have to properly dot these two vector quantities. Okay, you should know that here you have Q 4 pi epsilon naught r square r unit vector dot product with what is the spherical equivalent spherical differential displacement. You have r you have dr r direction plus r d theta theta direction plus r sine theta d phi direction. Okay, so you know in the dot products the orthogonal will produce 0, whereas in the those that having same direction like will be 1. Okay, here cos 0 cos 90. Okay, this one will will obtain 0. This one is 1. This one is in parallel, so we take this one. Okay, because it will result in 1. Okay, these two will result in 0. So your VAB is actually, when you further expand, you will obtain Q 4 pi epsilon naught of 1 over RA minus 1 over RB. Now if you notice, it is change position, right? Okay, you can see now, right? Okay, due to this. Okay, So this you obtain through the integration, okay? The integration of E with this, okay? If you observe from this, the question is asking the potential difference, right? So from point A to point B, okay? So from here to here, you can see, you can still get a you can still move from A to B from using this path. You can also move from A to B, for example, from this path. And you can also using this path. So if you notice, it is independent of path, okay? So as you know, VAB, potential difference, is measured in volts, okay? This one general, everyone knows. But the others is actually is joule per coulomb, okay? So why is it like this? Remember from the definition, okay? Work done, coulomb, okay? Joule per coulomb. Work is in joule and charge in coulomb. So don't mix up with the units, okay? If the question is asking work done, your answer should be in joule, okay? Next, we have from here this VAB potential difference. We can also know that VAB can be VB minus VA. If you have this in one subscript term, okay, one subscript, this one is actually called as potential. Or also known as absolute potential. Okay, what does it mean by absolute potential? Okay, let me further discuss on that. So potential, we will be, when we do a calculation, we will use a reference, okay? So it is common to choose infinity as a reference. Here, we may make assumption that the potential at infinity is 0. Potential at infinity is 0. Okay? Thus, if we imagine that we are bringing the charge, okay? If we are bringing a charge from infinity towards a location, for example, in this equation is B, so, and it is zero potential at infinity. So you can imagine that VAB, VB minus VA, and it is here is at infinity, and assuming potential at infinity is 0, so your VA equals to 0, because your RA is at infinity. So here you will have your VAB you will have your VB, okay? Is your RB approaching your R, okay? Simplifying this, then you have V equals to Q 4 pi epsilon naught R, okay? So when you have question that making the assumption that zero potential energy, zero potential at infinity, so straight you will lose these terms, then you only use one single terms, okay? With referring for the same here, okay? If you imagine, if you have your E and dl, and the charge is moving from infinity to a certain radius, okay? Imagine if it's radius of B. So you have your negative here, okay? See your negative there? So if we assume zero potential at infinity, the potential at a distant r from the point charge is the work done, okay, the work done per unit charge by an external in transferring a test charge from infinity, for example, let's say infinity here, for example. So your zero potential at infinity is that the potential when you are trying is a work done when we are trying to carry a unit charge, okay, unit charge from infinity towards that point. For example, imagine B, okay? There is situation, and it is not uncommon. Let's say your charge is not located at the origin, but it can be at any of these location, okay? So your potential for example, your charge can be here, okay, the point charge, or your point charge can be here, okay? So your V, okay, remember this is the case for the absolute potential, okay? If you have like for this is the standard one, so this one if we have the point charge at any location, so further expand it, you will have 4 pi epsilon naught, okay, in magnitude, okay, in magnitude r over r prime, okay. So here is the location, okay, this is associated, okay, this is actually location of your point charge. This is the location where we want to measure the potential, okay. So we will continue with one example. I will see you guys in the next lecture video, in the next simple exercise to help you understand problems associated with potential, okay. Thank you.